Hello guys, today I will make a video about the complex numbers and their usage in different mathematical fields. They can be used in combinatorics, algebra, number theory, and geometry as well. Let me start. What is a complex number? Complex number Z is a combination of a real number A and imaginary part Bi. The I is the number whose square equals to -1. So this can be represented as I equals root from -1. This looks like the Cartesian coordinate system, but there is one main difference. We got real axis and imaginary axis here. And if we know that z equals a plus bi, we need to take a unit on the real axis and b unit on the imaginary axis. So our point would be here, z equals a plus bi. And in most of the cases, complex numbers behave as the vectors. And now we will see what does this mean. If we got two complex numbers, z1 and z2, z1 equals a1 plus b1 times I, and z2 equals a2 plus b2 times I. If we want to take their difference or their sum, we need to add real parts to each other and complex parts to each other, imaginary parts to each other. So this would be z1 plus z2 equals a1 plus a2 plus b1 plus b2 times I. Similarly, we can make a multiplication operation. Z1 times Z2 equals A1 plus B1 times I times A2 plus B2 times I. And this equals A1 times A2 plus B1 times B2 times I square plus A1 times B2 times I and plus A2 times B1 times I. Now we can use the fact that I square, this is just -1. So this can be interpreted as a1 times a2 minus b1 times b2 plus a1 times b2 plus b2 times b1 times a2 times I. And to make a division operation, this is a bit complex, and for this we need to take the concept of conjugate. Conjugate can be represented as z and line above it. If z was a plus bi, the conjugate would be a minus bi. If you notice, this is just the reflection of complex number z over real axis. So we need to take negative bi here. So this would be z conjugate. So we know that conjugate of z is the reflection over the real axis. This has a lot of good properties. Now we will see them in the future. So the first and main property about the complex numbers and conjugate is like if we want to compute the magnitude of z, this equals a square plus b square, root from a square plus b square. And if you notice z times z conjugate, 1/2 root from here, this would be almost same thing and exactly same. Because this would be a plus bi times a minus bi square root. And we can see that a plus bi times a minus bi, this would be just a square minus abi plus abi minus b square I square. Now use the fact that I square equals -1. So this would be a squared plus b squared. So we have proved that if we want to find the magnitude of z, we just need to take the product of two conjugates and take the square root from this number. And now we can define what would be the division of two complex numbers. If we got a1 plus b1 times I, and this is divided by a2 plus b2 times I, now we need to multiply numerator and denominator both by the conjugate of the denominator. In this case, we will get the denominator as a real number. Now, let's see what would happen. a1 plus b1 times I times a2 minus b2 times I. And this is divided by a2 plus b2 times I times a2 minus b2 times I. And this would be equal a1, a2 minus b1 times b2 times I square plus a2 times b1 times I minus a1 times b2 times I. And if we notice denominator, this would be just a2 square minus a2 b2I plus a2 b2I minus b2 square times I square. We can once again use the fact that I square is just -1. So this would be equal a1 times a2 plus b1 times b2, because we got I square here, minus a2 b1 I plus a2 b1 I minus a1 b2 I over a2 square plus b2 square. Now we already know all the basic calculations about the complex numbers. And next one would be a bit hard homework or exercise. If you just take a plus I to the 2024 power, and now this is divided by a minus I to the 2025. Try to solve this equation. You can just pause the video for 10 minutes and I will start the solution after the 10 seconds. As always, we need to use the conjugates. So if we multiply both sides by the conjugates, what would happen? Conjugate of a minus I is a plus I. So we would have a plus I to the 2024 times a plus I to the 2025. And this is divided by a minus I times to the 2025 times a plus I to the 2020. Now we can use the conjugate formula. A minus I times a plus y. So let's see what is a minus I times a plus I. This would be just 1 minus I plus I minus I square. Once again, use the fact that I square is -1, so this would be just 2. So in above, we would have 1 plus I to the 2020, no, 4029, no, 49 power, and this is divided by 2 to the 25. And now define what would be 1 plus I to the 4049. If you just use the binomial expansion, this will be very hard to compute. So we need to find a bit easy computations. 1 plus I square, this would be 1 plus 2 times I minus plus I square. Because 1 plus I square, this is just 0, so this equals 2 times I. So our product can be represented as 2 to the 2024 times I to the 2024 times 1 plus I. And this is divided by 2 to the 25. From here, we can see that 1 plus, or we would get I to the 2024 times 1 plus I over 2. Then how can we compute I to the 2024? If we notice, if I is root from -1, then I square, this would be just -1. I cube would be I times I square, so this would be just -I. And I to the 4, this would be I square square, so -1 square. So we will get that this is 1. Similarly, we can notice that I to the 5, this is I to the 4 times I, and clearly this equals to I to the 6, this is I to the 4 times I square, so this would be -1. And clearly we can see the pattern that this is the periodic sequence whose period is 4. So we can see that 2024 is a multiple of 4. This means that I to the 2024 would be just 1. So the final answer would be 1 plus I over 2. So this was the basic calculations about the complex numbers. Next chapter would be about the polar form of the complex numbers. Next representation of the complex numbers is the polar form, and the difference between polar form and the regular form, which we already discussed, is that z can be represented as r times e to the I theta. There r is the real number, and theta is the angle which is composed between the real axis and these complex numbers. If z is this complex number, then this would be just theta. And the length of this line would be r. If we notice by using the right triangle property, all this k OB, OB, this would be just r times sine theta, and KB would be just r times cosine theta. And we can easily prove that r times cosine theta plus I times r sine theta, this is all exactly same what was A plus BI, because this would be A, and clearly this would be BI, which we have discussed in the first representation of the complex numbers. And how can we prove that e to the I theta, this equals to the cosine theta plus I times sine theta? To prove this, we need to use Taylor expansion of the series of e to the x, cosine x, and sine x. But I will not discuss this for today's video. If you will be interested, please write me comments and I will make another different video about Taylor expansion. And now let's look at what would happen if we take the product of two complex numbers, z1 times z2. This would be r1 times e to the I times theta 1 times r2 times e to the I times theta 2. And clearly we can see that this would be r1 times r2 times e to the I times theta 1 plus theta 2. From this expression, this is easy to notice that if we multiply two complex numbers, their magnitudes will be also multiplied. And magnitude of the z1, this is just r1, And magnitude of z2, this is just r2. And their magnitudes, like product of their z1 times z2, this would be just r1 times r2. So nothing will be changed, and clearly this formula is correct. And this equals magnitude of z1 times magnitude of z2. And what can be said about the angles? Angles are called also arguments. Argument of z1 is called the theta 1, and argument of z2, this is called theta 2. Argument of z1 times z2, this would be just theta 1 plus theta 2. And clearly this equals argument of z1 plus argument of z2. And clearly we have proved this property also. And what would be the conjugate of the z1 in terms of polar? Conjugate must have the same length or same magnitude, and the angle would be negative mark, like e to the I to the negative theta 1. So this is the main difference. If we got product of two complex numbers or division operations, it's better to write them in polar form. And if you got summation or subtraction of two complex numbers, it's better to write them in a plus bi. And now let's consider how can we add two complex numbers by the geometry rules. If you got one complex number here, called z1, and the second complex number z2, to make z1 plus z2, we need to use the parallelogram rule. z3 would be the sum of the two complex numbers, z1 plus z2, if this is the vertex point of the parallelogram, which is composed by the vectors of which are parallel to z2 and z1 from points z1 and z2. So clearly we can see that this is parallelogram rule, and if we want to compute the z4, we need to use the parallelogram rule for the same thing. If this equals z1 minus z2. And now let's consider what would happen if you got product of two complex numbers. If this was z1, who has angle theta 1, and this was another complex number z2, who has length theta 2, their product z3 would be somewhere here, which would have angle theta 1 plus theta 2. So this would be z3. z3 can be represented. If the magnitude of z2 was r2 and magnitude of z1 was r1, r2 times r1 times e to the I times theta 1 plus theta 2. So this was the all basic calculations about the complex numbers and their two different forms. Next chapter would be about their usage in the quadratic equations. Final chapter in this video about the complex numbers would be about their usage in the polynomials. How can we define the roots in terms of complex numbers? Let's consider any polynomial. X squared plus 5x plus 100 equals to 0. We can easily see that this doesn't have any real roots. So if we use the discriminant formula, we would get negative 5 plus or minus root from 25 minus 400 over 2. And this equals negative 5 plus or minus root from negative 375 over 2. And if we take the root from 375, we would get this equals negative 5 plus or minus root 375 times I over 2. And clearly we can see that these two numbers are conjugates of each other. If we define x1, -5 minus root 375 times I over 2, this one root, and the second root would be x2 -5 plus 370 root from 375 or I over 2. If you look at the coefficient of the I terms, they would be opposite marks. So this means that x2 equals the conjugate of x1. And similarly, x1 is the conjugate of x2. If you notice, if you are given any real coefficient polynomial whose degree is 2, their roots must be conjugate of each other. And now, if you use the fact that x to the n has n roots, x to the n equals 1. This has n roots. Now we need to use the polar form of the complex numbers. So if we define the cycle, unit cycle, and because we know that z1, like z to the n, magnitude of z to the n equals magnitude of z to the n, and this must be 1. This means that magnitude of z must be 1. So this point, this complex number must be on the unit cycle. So the remaining part is to define what would be the angle to this alpha. If z can be represented as 1 times e to the I theta alpha, I alpha, z to the n, this would be just 1 times e to the I times n alpha. And clearly, n times alpha must be a multiple of 2 times p. 2 times pk must be n times alpha. So alpha can be represented as 2pk over n. And clearly we can see that all these roots can be generated if we make alpha 2 times alpha, 3 times alpha, 4 times alpha, and so on. And last step would be, this would have negative alpha angle, or n minus 1 times 2pk over n. This would be the last complex number whose nth power would give us 1. And clearly 1 to the n would give us 1. These roots are defined like epsilon, and they can be represented e to the I times 2pk over n. And sometimes they are called nth root of unity. You can also similarly solve the equations if you got x to the n equals -1. In this case, instead of 2pk, you must take 2pk, 2 pi k plus pi. This must be n times alpha. And you just need to divide both sides by n to get what must be alpha. So this was all the facts which I wanted to consider for the complex numbers for today. If you will be interested about some topics about the complex numbers, please write in the comments, and I will try to make another video about them. And it is worth to mention that complex numbers are very useful, especially in physics. If you want to compute some of the hard integrals, you have to learn complex numbers very well. And at the end of the video, don't forget to like and subscribe my videos.